All right, my people, hello and welcome to week 15. Well, if this were a normal semester, we would be doing the last week of classes right now, and then next week would be final exam week. So what we'll do this week is I'm going to give you a discussion video on streams and rivers and running water on the surface of the earth. And so here we go. Well, you've seen this before. This is the Chippewa River. We did this when we did Google Earth. So we call it the Chippewa River, but as a earth scientist, what I really want to call it is a stream, because the definition of a stream is this. Any water that flows in a channel is called a stream, and it doesn't matter how big or small it is. We're talking about the Mississippi River is scientifically a stream. Okay, just like the Chippewa River is really a stream. We call it river when we're not talking scientifically. Okay, well, rivers, streams, have features called a watershed. A watershed is a piece of real estate, which is when a drop of water flows, or when a drop of water falls on the land, it will eventually make its way into a stream channel, and then maybe it'll be carried out into the ocean eventually. So let's take a look at a watershed. And every stream has its own watershed. And watersheds are separated by divides. So here's a map of the United States. The biggest watershed in the U.S. is the Mississippi River watershed. So if you take a look at this light blue here, all of this, if a drop of water falls anywhere in this space, it will eventually make its way into the Mississippi River, and it will drain into the Gulf of Mexico. Okay, look over to Florida and places like that. Any water that falls here is going to make its way, some of it will make its way into the Gulf of Mexico, and some of it's going to drain into the Atlantic Ocean. All right. If a drop of water falls here in Georgia by Atlanta, it's not going to make its way into Tennessee. That would mean it would have to flow uphill. Well, look up here at the Great Lakes. The Great Lakes, if a drop of water falls in Michigan, it's not going to go to the Mississippi River and the Gulf of Mexico. It's going to go in a different direction. Let's get a little bit of a closer look at the Great Lakes watershed. So what we see here is where a drop of water falls and what Great Lake it's going to go into. So here we are in Mount Pleasant. A drop of water that falls on us here is eventually going to end up in the Lake Huron. This yellow patch here is the Lake Huron watershed. All right, if a drop of water falls to the south of that, it's going to end up in Lake Erie. So all of southeast Michigan, Metro Detroit and all that, is in the Lake Erie watershed. And here is Lake Michigan's watershed, and here's Lake Superior's watershed. Here's another view of that, in fact, and that's in more detail. Now take a look at the individual watersheds within the Great Lakes watersheds. Okay, so this is the Chippewa River and the Tittabawassee River watershed, Muskegon's watershed, and so forth. If we get an even closer detail, we can see the individual streams. Here's Chippewa River, here's Tittabawassee River, there's the Shiawassee River watershed. So each polygon here is showing you an individual stream channel's watershed. Well, flowing water on the surface of the earth makes patterns, carves patterns into the shape of the land, and those patterns are controlled by the shape of the land. We call this drainage. Drainage, water moving through stream channels. And let me show you 4 types. And here they are. We'll take them one at a time. The first and most common kind of drainage pattern is called dendritic. Dendros is a root word meaning tree, and we call it dendritic drainage because it looks like a tree, branches of a tree. Now in this image, water is flowing from the smaller branches and meeting up and making larger branches. All right, so the small branches are way up in the highlands, And as these tributaries, branches of a stream, meet, they form larger and larger channels, essentially the trunk of a tree. So where do these things occur in nature? Well, let me show you one of these here. We're going to take a trip to... All right, here we are in Nevada. Las Vegas is down here. We are going to go to this place called Coal Valley, and we are going to look at the patterns of drainage on the surface here. Now, this is dry, and it's dry most of the time. When it rains here, it will dump about 2 inches of rain all at once, and then it won't rain again for the rest of the year. And this is what a dendritic drainage pattern looks like. So kind of a tall, skinny looking tree, but nevertheless, these branches, and just to give you a sense here, up here is higher ground because the mountains are over here. Water flows from the left to the right in this image, and the streams collect together from small branches into larger branches, and they make their way downhill and meet in a fairly large branch here. And that branch meets another large branch, and there you have it. Okay, so that's dendritic. And interestingly enough, Earth is not the only place we find these. We've found evidence of dendritic drainage patterns on Mars. Check it out. This is the side of a crater, and water doesn't flow on Mars now, but it sure did in the past. Check that out. That's some pretty classic dendritic drainage patterns there. All right, the second type of drainage we're going to talk about is radial. And radial meaning drainage that comes out of a central point. So when you have a pointy mountain like a volcano or some other kind of isolated peak, you're going to see these streams come out of a center point and radiate outward from the point of a volcano. And now you're looking at this and you're thinking, hey, wait a minute, you just told us about dendritic, and these sure do look like dendrites to me. And you're right, yeah. But they're all coming from the central peak of the volcano. So that's radial drainage. So here's where we could see that in nature. Here's an example of that. This is Diamond Head Volcano in Hawaii. All right, here's Hawaii. Okay, so this is Diamond Head Volcano. Now you're saying, okay, that's not a central point. No, but you are seeing this circle here, which is the crater of the volcano, and then there's streams draining out from the sides in all directions. All right, so radial drainage. Okay, great. Well, what about our third type here? And this is rectangular. All right, what's the deal with this? Well, if you see these streams, they meet at more or less 90-degree angles. So there's this main branch here, and it's being fed by these other small branches. Now, what causes that? Well, rectangular drainage you find on landscapes that tend to be like old. And when I say that, that means they've been sort of exposed and eroded for a long period of time. Like you think about the flat parts of... So type 4 we'll talk about today is trellis. And why do we call it trellis? Well, you think of a trellis as one of those wooden lattices that you put up to hold your vines or whatever, okay? A trellis kind of drainage is found in places where there are long ridges separated by valleys, and water will flow through those valleys. So take a look at this. Here is a place in Virginia in the Appalachian Mountains, and let's zoom in a little bit here. Here's a long ridge, and here's another long ridge, and so water will flow through them, in through the ridges, but there will be gaps in between the mountains where water can go across and into a larger stream. So the pattern looks like this. That's a trellis drainage. Right, check this out. This is a stream channel and see how it goes back and forth like that. Well, it meanders all over the place, and this is called a meandering stream. You get these kinds of streams in places where the landscape is flat, and instead of flowing across hard rock, it is flowing over basically sedimentary rock, like what we live on here in Mount Pleasant and in Chicago and Detroit and Louisiana and places like that. We're not sitting on solid rock. So water will flow, and water seeks the lowest part of the land because it wants to use the least amount of energy possible to flow. And here is what it looks like. Now, what carves these meanders? Well, it helps to take a look at a cross-section of a flowing stream, and here it is. And what I want you to see here is that the water does not flow at the same speed in a stream channel. And if you've been kayaking or tubing or on a fishing boat in a stream, you know this, because if you want to go faster, you go to the center of the channel. What causes the speed difference? Well, friction. When the water that's next to the bank is experiencing friction, so it gets slowed down, but the water in the center of the channel is free to flow. What this ends up doing is creating a spiral flowing pattern. So I want you to think of that water flowing to you in this picture, but in a corkscrew kind of way. And that causes erosion to be different on different sides of the channel. Take a look at this. So here is a view of a meandering stream, and we're going to pay attention to the continuous channel that goes from the bottom to the top. Here it is in a drawing. All right, so what we've got is we've got water, and look at the red line here on the diagram on the right. This is the fastest part of the water flowing through the channel. What happens is that on this side, this right here is called a cut bank, and there it is over there also. What happens here is that water, as it goes around on an outside bend of a channel, will pick up energy and it will erode the cut bank. But at the same time, see how the red line here is very far away from this part of the bend. This is the inside bend, and it is called a point bar. So water, the fastest part of the water is farthest away from here, so it loses energy, so it deposits the sediment it's carrying. So that means we're cutting over here, and we're building over here. We're cutting over here, and we're building over here. So this part of the channel is going to migrate towards the right, and this part of the channel is going to migrate that way. All right, so what's the deal with these things here? These sort of looks like they're meanders that have been cut off. Well, that's exactly what they are. They're meanders that have been cut off. So the water used to flow this way, this way, this way, and then it went into here, and then it turned around and it flowed back this way and kept on going, and then flowed into here, went around and came back and met the channel here. It doesn't do that anymore. Why not? Well, when a curve, a meander in the river gets too tight, like this part right here, the water slows way down, and any sediment that it was carrying, it doesn't have the energy to carry that sediment anymore, and it just drops. And that chokes the river, and the water can't flow anymore. And when that happens, the water in that channel, that curvy channel, gets cut off, and it's no longer connected to the flowing river. The water says, I'm not going through there, it's too low energy, I'm gonna jump right across over here and flow this way. And sure enough, it does. So these things are called oxbow lakes. Well, where's that name come from? It's an old-timey word back when people used to use ox, kind of like cows to pull wagons and stuff like that. They would put these bow-looking things over the necks of the ox and they could pull the wagon. Okay, so we still call them that, Oxbow Lake. Sometimes you'll see when you're out fishing or you're in the backcountry, you'll see signs for things called like Half Moon Lake. Don't see that too much in Michigan, but I sure did see it a lot down in the deep south when I lived there. So they call these things Half Moon Lakes or Oxbow Lakes. They are water that is not connected to the flowing stream, but there's still water in it. Now, when this stream floods, the water will spill out of the stream channel, the straight stream channel, and it will flood the landscape because all the land next to the stream is called the flood plain, and then that oxbow will get filled up too, and so that's how you can keep water in it. And it's also fed from groundwater. All right, let's talk about flooding and specifically how we try to understand floods. Well, let's talk about some terminology. We're going to talk about flooding in terms of discharge. That is, how much water is flowing in a channel or outside of a channel per second. And the unit is cubic feet per second. And that's because of how we calculate discharge. So a discharge is calculated by finding a channel and multiplying. You got to measure its width, you got to measure its depth, and you got to measure its velocity. So let's take an example of a river. Here's one. It is about 100 feet across. This is the Washita River in northeast Louisiana. In this particular location, it's 100 feet across, and it's 40 feet deep. And it's flowing kind of slow. It's flowing past me at about 6 feet per second. So what do? Well, you multiply those numbers. 100 feet times 40 feet times 6 feet per second. Well, that gives you 24,000 cubic feet per second. So you stand on the banks of this stream channel, and 24,000 cubic feet of water are going by you every second. And how many gallons is that? Well, it's about 180,000 gallons. Okay, so that's the Washita River when it's not flooding. So let's talk about floods specifically. And let's talk about the term 100-year flood. Okay, 100-year flood. Well, we have to worry about a 100-year flood, blah, blah, blah. What does that mean? It does not mean that a certain flood will happen every 100 years. It's like, well, we'll look at your watch. What time is it? Well, time for the 100-year flood. No, it doesn't work like that. A 100-year flood means this. A 100-year flood is the largest flood expected to occur in any 100-year period. It also means that for any year, this year, next year, 2024, whatever, for any year, there is a 1 in 100, also 1%, chance that this flood will occur. Okay. This is statistics fundamentally. Let me say a quick word about this, all right? Why do we use statistics? Well, because we are trying to put human rules on natural processes, right? We are a part of nature. And in order to live our human lives in nature, we need to have some ability to predict nature. So we use statistics. And a lot of the time, nature and statistics are cooperative. Sometimes, though, nature doesn't give a crap about our statistics and gives us the finger and does what it wants, and that's why we get flooding. So we have insurance companies, we have attorneys, we have people who like to build on the banks of stream channels. So what we try to do is for every stream channel, we try to estimate the probability of a flood in any given stream. So the way we do that is we do it mathematically, and we come up with an equation. And here's the equation, then I'll explain what the terms mean. Okay, R equals, parenthesis, N plus 1, close parenthesis, and then you divide that whole thing by letter M. Okay, what are these terms? Here they are. Okay, R is the probability of a flood. What's the probability of a flood? Is it a 100-year flood? Is it a 50-year flood? Whatever. N, I guess we'll make that lowercase, N is the number of years we have records for a given stream channel. And I'm going to show you examples of that in a minute. Okay, and M is the ranking of the flood, like the first worst flood, the second worst flood, the third worst flood, and all that. All right, so let's look at some stream data. This is coming right out of the assignment I'm giving you. Okay, here is stream data for a particular channel. And it's a river in California. And what I want to show you is all of the records. All right, so we have a column for years. We have a column for discharge, peak discharge. Okay, how much was the flood? In this particular stream channel, it was 93,000 CFS. So it's a smaller channel, but that's a bad flood. In fact, that was the worst flood. So the worst flood occurred in 1997. All right. When we do our math, we are actually not going to use these numbers, all right, for our calculation to solve R. So I want to solve R, and what I need is I need to know N. And what is N? Well, remember, N is the number of years we have records. So how do you figure that? How to figure this? All right, find the records. We got them. Find the oldest year. And then find the most recent year. And then subtract oldest from most recent. Okay, well, let's see. 1997, I don't see a year more recent than that. 1907, I don't see a year older than 1907. So, okay, well, then let's see if we found the records. 1997 minus 1907 is equal to 90 years. So therefore, in my example here, N, oh, look at that, N is equal to 90. So, all right, fine. How often is this kind of flood going to occur? All right, well, here's the math. All right, so we have our N. N, we know, is equal to 90 years. All right. What is M equal to? Well, what are we solving for? We're trying to find the worst flood, and that's 1. Okay, fine. M is equal to 1. So here's our equation. Our equation is R is equal to, parenthesis, N plus 1 divided by M. So we fill this out some more, then we get 90 plus 1 divided by 1. Then R is equal to 91 divided by 1. Therefore, R is equal to 91. All right. So that's the probability in years. Okay, 91 years. What is the, here's what this means. This means that this worst flood on this river should happen no more frequently than once every 91 years. We hope. Now, again, nature could be pissed off and say, I'm going to flood however often I want, but that's the frequency we expect. When we want to charge somebody home insurance, we figure, okay, when was the last flood? 1997. That was almost 25 years ago. Okay, we're going to charge you this amount based on probability R that we calculated. So, what is the percent chance of this flood occurring in any given year? Okay, well, and the formula for that probability is equal to 100 divided by R, which in this case, 100 divided by 91. Well, we go over to our handy-dandy calculator here, and we divide 100 by 91, and we get a P of 1.09. And what this means is there is a 1.09% chance of this flood occurring in any given year. All right, so I'm going to have you do the rest of these. I want to know what the probability is and the percent chance in any given year is. Okay, you're going to keep using R equals n plus 1 over m. So, helpful hint here, you're dealing with the same set of records. You're dealing with the same oldest year and the same most recent year. That means for every one of these calculations you're going to do, n is going to continue to be 90. It's so easy, it's almost busy work, all right? What I want you to do with each one of these is I want you to put them into words. So you're going to scroll down to number 2 here, and you're going to say, all right, okay, write 2 sentences for each year. The first sentence writes out the percent chance of this discharge flood happening during any year, and then how often this flood will occur in years. Okay, so I'm going to do it like this. For m equals 1, the percent chance of this flood happening in any given year, come on, is 1.09. In fact, I don't even need the word percent here. The chance of this flood happening given is 1.9%. This flood should occur every 91 years. Okay. You're going to see this sentence I wrote? You're going to write 2 sentences like that for every single one of these you calculate. All right, and that's it. So what you're going to do is you're going to download this sheet from the Google Drive. You're going to put your name on it. You're going to save it as your last name, and you're going to shoot it back to me. You can stick it in the folder. You can send it in an email. You can do it by hand and take a picture of it with your phone. I'm happy with that. Just get both sheets, all right? All right, just to boost your confidence in an era of shelter in place, I'm going to do one more for you just to make this simple here. Okay, so I'm going to do the worst flood I see on this, which is the M of 60. All right. Now, so I got to do the R equation. R equals n plus 1 over m. Same n. Same river, same sheet full of data. Okay, so R is equal to, oh crap, what was that? 90, duh, and then, all right, 90 plus 1, and that whole thing is divided by, I gotta put my parentheses, all right, divided by m, which I looked and know that it's 60. Okay, so R is equal to 91 divided by 60. R is equal to, hold on, I got to get the calculator out here, 91 divided by 60. Oh, okay, look at that, 1.51. So, great. R is equal to 1.51 years. Okay, and now I got to do the percent chance. Percent chance, P is equal to 100 divided by 1.51. So, what does P equal to? Let me get out my calculator again. 100 divided by 1.51. Okay, 60, whoops. Well, that's a 66.2. I'm going to round it up to 5. All right, 66.25. Okay, now I got to put these in words. Okay, so I'm going to go down here. For m equals 60 chance of this flood happening in any given year is 66.25%. This flood should occur every 1.5 years. See how I rounded? I rounded. Okay, you can do that. Now, you're going to do all of these others in between, and you're going to put those sentences in between, and you're going to shoot this back to me. Okay, that's it. That's our show. That's streams, and that's the work I want you to do for this week. All right, hang in there, people. If you need anything, get a hold of me. Remember, the due date is breakfast time on May 13th. That's when I need this stuff. So, you know what? Don't freak out on me. Hang in there. If you need help, if you need anything, if you need, whatever, just send me an email. You call my office number and it comes to my email, but I want you to be okay. All right? See ya.
Oh no, we're gonna rock down to Electric Avenue, and then we'll take it higher. Oh, we're gonna rock down to Electric Avenue, and then we'll take it higher. Working so hard like a soldier, can't afford a thing on TV. Deep in my heart I abhor ya. Can't get food for the kid. Good God, we gonna rock down to Electric Avenue, and then we'll take it higher. Oh, we gonna rock down to Electric Avenue, and then we'll take it higher. Oh no. Oh no. Oh no. Oh no. Oh Lord, we're gonna rock down to Electric Avenue, and then we'll take it higher. Oh, we're gonna rock down to Electric Avenue, and then we'll take it higher. Who